Hey everyone, how are you doing? Welcome back to Interview Forge. Today we're designing a real-time chat system. Think WhatsApp, think Slack. This is one of the most commonly asked questions in Mang interviews. And every chat app interview has one question that separates a 6 out of 10 from a 9 out of 10. It's not which database. It's not how do you scale. It's how do you guarantee message ordering across distributed servers. By the end of this video, you'll know the answer. Let's go. So the question is, design a real-time chat system, something like WhatsApp or Slack. Users should be able to send one-on-one messages in real time. Support group chats with up to 500 members. Show online status and typing indicators. Messages should persist, even if the receiver is offline. And it needs to handle 50 million daily active users. This is a top 5 most asked system design question, and most candidates treat it like a simple CRUD app. It's not. Before we touch architecture, let's log down our numbers. First, message volume. 50 million daily active users. If each user sends an average of 40 messages per day, that's 2 billion messages daily. About 23,000 messages per second. That's our write throughput. Second, read volume. People read way more than they write. They open chats, scroll history, check multiple conversations. Let's assume 85:1 read to write ratio. That's 115,000 reads per second. Read heavy, just like the URL shortener. Third, whale message size. Average message is around 100 bytes of text. 2 billion messages times 100 bytes. That's roughly 200 gigabytes of new data per day. Over a year, about 73 terabytes. We'll need a storage strategy that handles this. Fourth, latency requirements. Real time means real time. Message delivery needs to be under 200 milliseconds. Anything above 500 million users, notice the lag. 4 requirements, clear numbers. You're already ahead of 70% of candidates. Define your APIs before architecture. You know the drill. First, a WebSocket connection endpoint. This isn't REST, but it's a persistent bidirectional connection. The client connects to .udit chat, authenticates with a token, and keeps the connection alive. This is how messages flow in real time. Second, post API v1 messages for sending a message. The body includes conversation ID, message text, and message type. But here's the thing. In practice, messages go through the WebSocket, not REST. The REST endpoint is a fallback for when WebSocket drops. Third, get elaborate APv1 conversations for listing a user's conversations, returns conversation ID, last message preview, unread count, and timestamp. Paginated, sorted by most recent activity. Fourth, get APv1 messages with a conversation ID parameter. Returns message history. Cursor-based pagination, not offset-based. Why? Because new messages keep pushing the offset. Cursor pagination is stable. And fifth, put APv1 users at status for presence updates. Online, offline, typing. These are lightweight but high-frequency events. Quick checkpoint. Requirements plus API design. That alone puts you at 3 out of 10. Most candidates don't get here until minute 20 of the interview. You did it in under 2 minutes. Let's keep stacking. Now the architecture. Every component earns its place, starting with clients, mobile and web. They maintain a WebSocket connection for real-time messaging. Next, a WebSocket gateway layer. These are stateful servers. Each one holds thousands of active connections. This is fundamentally different from a stateless REST API. The gateway knows which user is connected to which server. Behind the gateway, we need a connection registry. This is a fast lookup store. Redis works perfectly here. It maps user IDs to their WebSocket server. When you send a message to someone, the system checks which gateway server is this user connected to. Redis answers that in microseconds. Message service sits behind our gateways. It handles message validation, persistence, and routing. It's stateless. Any instance can process any message. For storage, we need 2 things. A message store for persistent chat history. Cassandra is ideal here. I'll explain why in a moment. And a cache layer for recent messages and hot conversations. Finally, a notification service. When the recipient is offline, no active WebSocket connection, the message still needs to be delivered. Push notifications via APNs and FCM handle this. 6 components, each one justified. Let's go deeper. Let's trace a message from send to receive. This is where it gets interesting. User A sends a message through their WebSocket connection. It hits gateway server 1, the gateway forwards it to the message service. The message service does 3 things simultaneously. writes the message to Cassandra for persistence, updates the conversation's last message in cache, and looks up user B in the connection registry. Let's say user B is connected to gateway server 3. The message service publishes the message to a message queue. Gateway server 3 picks it up and pushes it through user B's WebSocket. Total time from send to receive, under 100 milliseconds. But what if user B is offline? No WebSocket connection found in the registry. The message service flags the message as undelivered and triggers the notification service. When user B comes back online, the client fetches all undelivered messages via the REST API. This dual path, WebSocket for online, push notification plus REST for offline, is what makes the system reliable. If you've made it this far, you already know more than most candidates who walk into this interview. But the next part, data model and scalability, is what actually gets you the 8. Stay with me. Why Cassandra for message storage? Messages are append-only. You write them once, read them many times, and you never update them. That's a perfect fit for Cassandra's append-only write model. The partition key is conversation ID. The clustering key is message timestamp in descending order. This means fetching recent messages in a conversation is a single partition read, blazing fast. The messages table, conversation ID as partition key, message timestamp as clustering key descending, sender ID, message text, message type, and a status field, sent, delivered, or read for conversations, a separate table. User ID as partition key, so you can quickly look up show me all conversations for this user. Conversation ID, last message, preview, unread count, and updated at. The read receipts trick, when user B reads a message, you update the status to read and send a lightweight event back through the WebSocket to user A. That's the double blue check mark. Group messages add a fan out problem. When someone sends a message to a group of 200 people, you need to deliver it to 200 WebSocket connections. Two approaches, write fan out and read fan out. Write fan out means you copy the message into each user's inbox at right time. Fast reads, but write amplification is massive, 200 writes per message. Read fan out means you store the message once and each user reads from the group's feed. One write, but reads are slower. For groups under 500 members, read fan out wins. One write to the group's Cassandra partition, each member reads from it. Simple and efficient. Presence, online status and typing indicators. These don't go through the message pipeline. They're ephemeral events sent directly through WebSocket. Online status uses a heartbeat. The client pings every 30 seconds. Miss 2 heartbeats, you're offline. Store presence in Redis with a 60-second TTL, lightweight and fast. Checkpoint, architecture, message flow, data model, group chat. You're at 6.5 out of 10. The next section on scalability is worth 2 full points. This is where you go from good to great. 3 scaling challenges you must address. First, horizontal scaling of WebSocket servers. Unlike REST servers, WebSocket connections are stateful. You can't just add servers. You need sticky sessions or a connection-aware load balancer. Consistent hashing on user ID works well here. Each user always routes to the same gateway server. Second, cross-server message delivery. User A is on gateway 1, user B is on gateway 3. How does the message get across? A pub sub layer. Redis, pub sub, or Kafka. Each gateway subscribes to a channel. When a message needs to reach a user on a different server, it gets published to that server's channel. The gateway picks it up and pushes to the right WebSocket. And third, here's the question I teased at the beginning. How do you guarantee message ordering across distributed servers? The answer, use a monotonically increasing message ID per conversation. A Snowflake ID, timestamp in the high bits, server ID in the middle, sequence number in the low bits. Messages are always sortable by this ID, regardless of which server generated them. And on the client side, the UI sorts by this ID, not by arrival time. That's how WhatsApp does it. That's how you answer it. Final score. Requirements gathering, 9. API design, 8.5. Architecture and message flow, 9. Data model, 8. Scalability and trade-offs, 8.5. Overall, 8.7 out of 10. That puts you in the top 12% of candidates. The average score on this question is 4.8. You just doubled it with structure. If this helped, hit like and share it with someone who's prepping. It genuinely helps the channel grow. Want to practice this exact question by actually speaking your answer out loud? Interview Forge scores you in real time across 5 dimensions. 3 free sessions every day. No sign up needed. Interviewforge.dev, link in the description. Next video, we are designing a rate limiter. Subscribe so you don't miss it. Drop your score in the comments. Who beats 8.7?